Okay, great. So we're going to be doing problem number 24 from the book. And so, from section 5.3, I should say. And so in this case, we have a matrix which happens to be lower diagonal, which is really nice. And why this is nice is it actually makes our calculations very straightforward. So 0, 0, 0. Because what we're looking to do is find the eigenvalues and eigenvectors of this, and the dimensions of our eigenspaces. And so, if this is our A, when we do A minus lambda I, and take a determinant of that, it gives us that same matrix, subtracting these lambdas off the diagonal. Then we have these other numbers hanging out, but they're not doing a whole lot because when I take the determinant here, so use that determinant notation, I'm just going to expand across the top row. So this would give me a 1 minus lambda times the determinant of that lower sort of 4 in the bottom right corner, which would be 3 minus lambda, negative 2 minus lambda. And that's all I have. So notice this is, sure it's cubic, but it's already in factored form. All our work is done, which is really, really helpful. So we say lambda then is equal to 1, 3, or negative 2. So we have these three different or distinct eigenvalues, and we want to find the eigenvectors for these. So notice whenever we do that, if we're plugging in each of these, we're going to lose one of our elements there. So let's say we plug it into plug in lambda 1, we'll call the first one. So that gives us this matrix, which is 0, 0, 0, negative 1, 2, 0, 3, 2, negative 3. And so I want to know, if I multiply this by some vector, I want to get the 0 vector. And I want to find out what this v could be. Right? I want to find something that's interesting, so not just the 0 vector. And so notice here, I'm just going to use a little bit of sagacity and say there is no repeated roots. So my guess is this is just going to be sort of one-dimensional thing. And so let's just pick a value. So looking at this, it looks like it would be okay if I just pretended that the first component of my vector I'm looking for was 1. If the first component is 1, then when I multiply it by this row, so this vector times this one, the second component will have to cancel. So the first component will be 1 times negative 1. So the next component would have to be a half to get that thing to cancel. And then when we look at the third one, if I did 1 times this, a half times this, so that'd be 4, minus 3. So this is kind of gross, but that would give you, that last element would have to be 4 thirds. So there's an eigenvector for it. If you want, you can multiply by 6 and get 6, 3, and 8. So far, so good. Now we're going to move on to the other eigenvalues. Great. So scrolling down a little bit, I guess before I hit play, I probably should just rewritten the matrix, but let's just do it again. So remember, we're doing our matrix, but this time we're going to go ahead and let lambda 2 be the number 3. So in our matrix, when we subtract 3 off the diagonal, I'd have negative 2, 0, 0. I have negative 1, 0, 0. I have 3, 2, and I also have negative 5. So I want to multiply this by some vector. Right, and notice when I do this, so if you consider the vector as like 3 components, v1, v2, v3, just elements, the v1 is always multiplying the first row, or the first column, v2 second column, v3 third column. And so that's like a nice way to visualize these things. But we just use this notation here. So this is going to be equal to 0. So we need to find some vector that does this. I could put this into a reduced relational form and whatnot, but notice, in order to make the first multiplication for the first row 0, I will in fact require that my first element is 0. That's the only way to make the first or the second one work. If you wrote this out as an equation with x, y, z, this would be like negative 2x is equal to 0. Yeah, clear x out of the picture. Likewise, that means this 3 right there. That's going to be 3 times 0, so that'll be out of the picture. I'm just going to go ahead and say, let's let our z be like 1, say. Or pick some number. If I see 5s and 2s, I might let it be like a 10, just to guarantee that I'm not going to end up with fractions. So you can do that if you want. Just pick some number for z. And then what would y have to be? Well, in order to make this bottom row work, the x component, so the v1 is 0. This one is negative 50, right? So then 2 times what would cancel out negative 50? So 25. So I didn't have to go that high. In fact, this one, it would have been just good enough to have also done 2 and 5 there. So notice the 2 and the 5 is just like those 2 and the negative 5 there, but switched in order and one has switched signs. So there's either one of these would be okay. I think I prefer this one. So there's another vector. So this is the eigenvector that corresponds to the eigenvalue of 3. Let's go ahead and do the last one. So if my last eigenvalue, which was, I believe, negative 2, notice in this case the eigenvalues do just show up on the diagonal, so it makes it pretty easy to know these. So in this case, I would have the matrix. So when you do 1 minus negative 2, you get a 3. Because I have a bunch of zeros. So that's going to make that first element 0 again. Negative 1, 5, 0. You have 3, 2, negative 2. Alright, so it would be 3, 2, and then negative 2 minus negative 2 is 0. Alright, great. Ooh, look at this. A column all zeros. That's going to tell me that Z is irrelevant. Z is your fun uncle who's off in the Bahamas. Like, he's doing whatever the heck he wants. And notice this, in order for this top row to work, x would have to be 0, right? Because 3x's is equal to 0, so x is 0. So my first element is 0. For this middle one to work then, if x is 0, this would be 0 plus 5y is equal to 0. So y would have to be 0 as well. And then z is doing whatever the heck it wants, so pick a number. You know, 1's nice, but heck, you can use square root of 7, whatever the heck you want. Just stick a number in there. So there's your third eigenvector. So any, well, listen to me, any vector that is just along the z-axis, if you multiply by this matrix, and in fact just multiplies it by negative 2. Great, so there you have it. We have found those all, and the dimension of each eigenspace. Okay, yeah, so the eigenspace corresponding to each of these, since they just had one eigenvector, is consistently one-dimensional.